Good morning, students. Let us start the AEC class. In the last class, we had seen some differences between BJT and JFET. Just to remind you, let me go back to the previous slide. Here you can see BJT is bipolar, having both electrons and holes. JFET is unipolar, having either electrons or holes. That is when we call the JFET as either N-channel JFET or P-channel JFET. Whereas we call BJT as either NPN or PNP. So BJT is a current control device because it is having IB and IC relationships, whereas JFET is a voltage control device. In BJT, the transfer curve is linear because there is beta. Beta is the ratio between IC and IB. As it remains constant, the transfer curve means output versus input. That particular curve will be linear. Of course, the device is non-linear. The device's input characteristics and output characteristics are non-linear. But the transfer curve is linear because of beta. Whereas in JFET, the transfer curve is non-linear because it is a voltage control device, and basically it is the gate to source voltage that is trying to turn on the JFET. There is no gate current, and as such there is no beta. That is how in case of JFET, the transfer curve means output versus input, that is non-linear. And you already know BJT is having three terminals called emitter, base, collector, and JFET is having three terminals called source, drain and gate. And as you already know, BJT is having three regions of operation called cutoff, active, saturation, whereas in JFET we have three regions of operation called cutoff, saturation and ohmic. Whatever is saturation in BJT, that we call it as ohmic in JFET, and whatever we call it as active region in BJT, we call it as saturation in JFET. And in BJT, emitter and collector are physically different, whereas in JFET, source and drain are physically identical. Now, with this brief recap, let me go to the next slide where there are some more differences listed. So, to go through some more differences between BJT and JFET. BJT has finite gate current, whereas JFET has BJT has finite base current, whereas JFET has no gate current. Because as such JFET is normally on, we are going to turn it off. Whereas in BJT, as such BJT is normally off, we are going to turn it on by supplying base current. In case of JFET, the device is normally on, we are going to turn it off by applying negative gate bias. So there is no gate current in JFET. And in BJT, there is finite input impedance. We had worked out some exercises in the first module about finding out the input impedance of different biasing circuits. And we have seen that it has some few kilo ohms of input impedance, whether it is common base or common emitter or common collector. Few kilo ohms of input impedance is there in case of BJT. We have already seen a model called RE model, and we had represented the input impedance in terms of beta into RE, that small RE. But in JFET, the input impedance is very high. The reason is there is no gate current, and the gate is being reverse biased for the device to be turned off. So naturally, when there is no gate current at all, input impedance is really very high in case of JFET. This is one of the primary advantages of JFET compared to BJT. In case of BJT, the input impedance can be few kilo ohms, whereas in JFET it can be few mega ohms. Now BJT is better as an amplifier because it has a large gain and it has a higher sensitivity because of base current. This we have seen. Whereas in JFET, this is better as a switch because it has a sharp curve. Please remember the output characteristics which I had shown earlier, where the curve is sharp means in the ohmic region it is having a finite slope, and later on in the saturation region it is almost parallel to x-axis. which means the curve is really very sharp when compared to BJT, due to which JFET can be used as a better switch. It is easy to turn it off and turn it on just by applying the gate to source voltage. And JFET has less temperature dependence. Why? Because JFET has no beta as such. JFET has no gate current as such. When there is no gate current, there is no question of increase in the bias current or something like that. So as such, JFET is having a lesser temperature dependence when compared to BJT. Now BJT is larger in size because collector has to be much larger, emitter has to be medium region, base will be much smaller. Whereas in case of JFET, it is a single channel and the channels to ends are called as source and drain, and they are interchangeable also. Physically, they are one and the same, and there need not be a difference between the areas of the regions. In fact, in BJT, there are three regions called emitter base collector. Whereas in JFET, there are only two regions. One is the channel in between and one is the gate area that is surrounding. There are only two regions. As such, the size of the JFET can be much smaller than the BJT because there is no source and drain distinctly separate area. That way, JFET can be fabricated as much smaller in size compared to BJT. Now, BJT is difficult to fabricate. Why? As you already know, collector is larger, emitter is medium region, base is smaller. In addition, collector will be medium doped, emitter will be heavily doped. So, doping wise also, area wise also, there are differences. That is why BJT is difficult to fabricate or to manufacture. The factories or industries where these electronic devices are manufactured, they are called as foundries. In India, we don't have a VLSI foundry, but we have a LSI foundry. That means we have large scale integration foundry at Chandigarh. There is one company called Semiconductor Complex Limited, SCL, that is at Chandigarh. So they can manufacture the MOSFET devices of having channel length up to 180 nanometer in size. But we are now in the era of VLSI, very large scale integration, where in fact in Chandigarh the foundry is also a VLSI foundry only, but it is 180 nanometer. But as such, now the device size of MOSFETs is come down to 90 nanometer, 45 nanometer, 22 nanometer and even 10 nanometer. Right now, Intel is working on MOSFETs which are having the channel length of 10 nanometer. Channel length simply means the gap between source and drain. That can be as small as 10 nanometer. Now think about this device which is so small. That is why earlier I had given you an example of your pen drive, where if there is a 4 GB pen drive, then 4 into 10 power 9 into 8 charge storage devices or MOSFETs have to be present inside a small pen drive. That is the power of very large scale integration, where this transistor is not at all visible to the human eye. The transistor, if it has to be seen, it has to be seen through the electron microscope, not even through the normal microscope, because the transistor is so small in size. But how do they manufacture transistor which is so small? Don't ask me the question now. You are going to study this when you come to 5th semester. You are going to study in detail about how the MOSFET fabrication happens in foundry. So in India, we don't have a foundry which can manufacture 90 nanometer and 45 nanometer. The reason is heavy investment is required and regular orders are also required. Whereas in China, they are famous for manufacturing electronic products. They are famous for manufacturing anything and everything as such. In the present scenario, they have become famous for doing wrong things also, of having a wet market and releasing virus and all such things. Otherwise, Chinese are very hard working people and they are experts in manufacturing electronic items or electronic products. So in China, there are full-fledged cities which are dedicated for manufacturing only the integrated circuits or only the electronic devices. So there they have the foundries where they can manufacture even a 90 nanometer, 45 nanometer, 22 nanometer, even a 10 nanometer device in future if required. So I am telling you about these foundries. Now if the device is of having easier design, then it is easy to fabricate. The process of fabrication is nothing but the process of manufacturing this device. Silicon wafer has to be taken, then the wafer has to be doped with the N-type and P-type, and then after doping, it has to be insulated, gate, drain source connections have to be taken out, or emitter base collector connections have to be taken out, and then it has to be packed to be used. There are very large physiochemical and electrochemical processes involved in manufacturing electronic devices. That process itself is called as fabrication. Just like in civil or in mechanical, we have this term called fabrication. Even in electronics, the manufacturing of the devices itself is called as fabrication. Now, BJT is very difficult to fabricate. Why? You already know, dissimilar regions, dissimilar doping. Whereas in JFET, there are no distinct regions as such. There are only two regions, channel and the gate, and source and drain are identical. So it is easier to fabricate. Compared to BJT, JFET is easier to fabricate, which means it is easier to manufacture. The last point between BJT and JFET is there is something called gain bandwidth product. When I discuss the amplifiers, I will go into more detail about this particular term. We have already calculated the gain for BJT amplifier circuits. We did not measure the bandwidth there as such. Bandwidth means the range of frequencies up to which the amplifier can work satisfactorily. No amplifier will have an infinite bandwidth. Even though ideally we want an amplifier should have an infinite bandwidth. That means from 0 till infinity with all frequencies it should work. But it cannot work that way because of some other limitations. What are those limitations? We are going to discuss in module 3. In module 3, we will be having a high frequency analysis of amplifier circuits. There you will come to know more about bandwidth. Now the term here means that we want to have more gain and we want to have more bandwidth, but that is not possible. If we design an amplifier with the larger gain, its bandwidth will come down. Now if we design an amplifier with the larger bandwidth, gain will come down. Don't ask me why. I am going to discuss this reason in the third module when we perform high frequency analysis of the amplifier circuits. So we cannot have both. Means we cannot have a gain which is much large and we cannot have a bandwidth which is much large. If we increase gain, bandwidth will come down. If we increase bandwidth, gain will come down. So for this purpose, we have some other techniques called feedback techniques, where we apply negative feedback such that when gain reduces, bandwidth will increase. But ideally, we want to have a much larger gain bandwidth product. Now, when we compare BJT and JFET, the gain bandwidth product of JFET is smaller and the gain bandwidth product of BJT is larger. So, in such cases, if at all we require an amplifier where we want to have a larger gain bandwidth product, we will have to go for BJT. Now, if we can compromise with a smaller gain bandwidth product, we can use JFET. It depends on the particular application. But as such, we can only have smaller and larger. We cannot have largest as such. That is the idea here. More about the gain bandwidth product will be discussed in module 3 only. Until then, you will have to wait. Let me go to the next slide now. we had seen the N channel device earlier. Now, on the contrary, we will have a P channel device. Of course, we will not be using P channel device much in our circuitry in this subject. In the 5th semester, when you study CMOS VLSI design, there you will see that both P channel and N channel will be used in a complementary fashion. Here we are discussing the P channel device only to have an understanding of the other counterpart. So you can see here, the channel is of P type, around which the gate is of N type. The gate material is N type, and as such you will see the drain is connected to the negative terminal. In our N channel device, we used to connect the drain to the positive terminal. Here, naturally drain has to be connected to the negative terminal. Why? The channel is of P type, source has to be now positive. Now the positive supply voltage will repel the holes, and all the holes will go towards negative. They will be attracted by the negative plate of the battery. That is how the battery power supply is just the reverse of that N channel. Now to tell you a small fact, holes do not exist as such. Basically, hole means a vacancy in the outermost orbit of the semiconductor, which means if an electron is deficient, then there is a vacancy for an electron. That vacancy will be positive charge. When an electron comes, that positive charge gets occupied by the negative charge. That is the idea. So holes do not exist as such, only vacancies exist or positive charges exist. Now if the hole has to be occupied, electrons from some other place has to come and occupy. Holes cannot move. Only electrons can move. Just like in the golf court, you will have a hole and you will have a ball. Now the ball will go to the hole. Hole will not move anywhere. In the same way, you visualize, electrons have to come to the hole and they should occupy the hole. Holes cannot move. But for the sake of illustration, we show as if holes are going to move. Okay, basically it is electrons only moving in the other direction. Now that is this P channel, and there you have the N-type gate. Now to the N-type gate, we are connecting a positive supply now. In the earlier device, we used to connect the negative supply to the gate. Now you know that this channel is normally on. If the channel has to be turned off, then the depletion layer has to come into a pinch off region, and for that purpose, the gate voltage has to be now positive. Now you can see that this N and P is actually reverse biased. For the transistor to turn on, what we have to do is, we have to reverse bias the gate to source connection or gate to source region. That is how whatever was the power supply connection in case of N channel, in case of P channel, it is simply the reverse. You can see its characteristic curve here. You can see now the x-axis is negative because drain to source voltage we have applied a negative voltage as such. X-axis is negative, and you can see the voltage versus current, VDS versus ID. This curve is similar to N channel, where we call this left side near the y-axis, we call it as ohmic region, and the bottom side near the x-axis we call it as cutoff region, and the other region we call it as saturation region. Now in the saturation region, device will be half on, half off. In the ohmic region, device will be completely on. Why? Because drain to source voltage, when it reduces, then it means that device is completely on, and in the cutoff region, device is completely off. Why? Because in the drain to source voltage is larger, it simply means that the switch is off. Please recall all the basics of BJT. The same concept is applicable here even in JFET. But in this picture, you will see at the right hand side one shaded region. This is called breakdown region. Breakdown region in the sense, If the drain to source voltage exceeds a certain limit, then the complete semiconductor material can get burnt out, because the small semiconductor material may not be able to withstand a much larger voltage. When it cannot withstand the much larger voltage, the complete material can burn out and the device will be damaged. That is called breakdown region. In fact, this breakdown region exists even for N channel also. Breakdown region exists for all the electronic devices, including diodes, including resistors, capacitors, inductors also, because the material which is used for manufacturing a device will have its own size, will have its own basic properties. We cannot apply a much larger voltage across any electronic device as such. It is like a load to a steel rod also, or it is like a load to a brick as well. Now, a small brick can withstand how much of load? That has to be tested by the civil engineers. A small steel rod can handle how much of load? That has to be tested by mechanical engineers. In the same way, a device can withstand how much of load? Here the load is nothing but current and voltage. Now that has to be taken care when we design the circuits. So in general, I had shown you the data sheets in the earlier module. I had discussed in brief about the data sheets, and there I had told that if in our power supply, if in our circuitry, let us say a device has to handle 10 volts, we will choose a device which is capable of handling 20 volts, which means that we will always select a device which is double the rating of our application. I had given an example that if my head can handle 100 kg weight, then I should not always handle 100 kg. I can safely handle 50 kg weight. Daily, if I handle 50 kg weight, my head is manufactured to handle 100 kg weight. That way, my head is safe. Same way, in the circuitry, if there is a voltage, we will choose a device which is capable of handling double the voltage. Otherwise, the device will break down if such situations come into picture. Okay, let me proceed. At high levels of VDS, the current suddenly rises, leading to breakdown region. Hence, care should be taken during design. See, when VDS increases, ID keeps increasing. That means when voltage is increasing, current is also increasing. That is natural, because this channel will have its own resistance. But if the voltage increases further, current may have an avalanche effect. Current may have a destructive effect, where current will suddenly rise, because this P channel or the N channel may not be able to handle that much of voltage. Suddenly the semiconductor will become conductor and the whole thing will be burnt. You already know that carbon, silicon, germanium, tin, lead are in the group 14 in the periodic table. We discuss only about silicon and germanium as semiconductors, but carbon is also in the same group. Carbon is also having 4 electrons in the outermost orbit. That is also having tetravalency. So anything when it burns, it becomes what? It becomes carbon only. Whenever whatever burns, it becomes carbon. Means if there is a high voltage applied, silicon may burn and silicon itself will turn out into carbon and that will break down. Therefore, care should be taken during design. Now, this phenomenon occurs with the N-channel devices also, but at a larger value than that of a P-channel devices. Breakdown occurs with the N-channel devices also, but that will occur at a larger voltage than a P-channel device. Why? The reason is there is something called mobility of electrons and mobility of holes. Mobility of holes is nearly 2 times lesser than the mobility of electrons. I don't know whether you have studied this in physics or not, there is something called mu n and there is something called mu p. Mu n is mobility of holes, mu p is mobility of electrons. Always the mobility of holes is lesser than the mobility of electrons. As I told you now, holes cannot move, electrons have to move now. That means electrons have to be pulled from somewhere and they should occupy the holes. So naturally, n-channel device will have a larger mobility of charge carriers when compared to p-channel device. That is because in n-channel device, electrons are present abundantly. Whereas in p-channel device, it is the holes that are present and holes cannot move. Electrons only have to move to fill the holes. Due to this reason, mobility of electrons or mu p is nearly half of that of mobility of holes. Sorry, I told wrong. Mobility of holes, mu p, is nearly half of mobility of electrons, that is mu n. That means mu n is equal to 2 into mu p, or mu p is equal to mu n by 2. Because of this, p-channel device will have breakdown at a lesser voltage when compared to the n-channel device. That's all. Look at the symbol of this n-channel and p-channel JFETs. At the left side you are seeing n-channel JFET, or at the right side you are seeing p-channel JFET. What does this mean now? Just look at the symbol and what does this mean? Now drain is positive, source is negative. We apply a battery supply across drain and source. Now you can see the drain and source are identical. Just relate this symbol along with the symbol of BJT and you will come to know that in BJT, I will have to admit these students who are waiting in the lobby. Okay, in BJT, emitter will have an arrow mark, collector will not have an arrow mark. But in JFET, you will see that drain and source are having the same type of line, which means there is no arrow mark here. Why? Because in JFET, drain and source are identical, so there is no need of distinguishing between drain and source. The top side generally we call it as drain, bottom side we will generate as source, and we collect the power supply to drain and negative of the power supply we connect to source. That is why it is mentioned here as D and S. But physically, drain and source are interchangeable, which means when you connect this device, even if you turn it upside down, the device will work. Which means whichever you are connecting to the plus, that you will have to call it as drain. Whichever you are connecting to minus, that you will have to call it as source. That's all. Otherwise, physically they are identical. That is why even in the symbol you can see the same. Now, for the n channel, gate will have an arrow mark like this, and the arrow mark is pointing towards the channel. What does it mean? This means that there is a PN diode between gate and channel. Channel is N type, gate is P type, so P to N is a diode. That itself is indicated by the arrow mark here. So if you understand the symbol, you will understand the device. Many times the people who design these symbols are genius people. I keep on telling that the people who design the symbols are really very genius. In the sense, let us say I will write the symbol of a resistor. I write the symbol of a resistor. Now, what do you understand by this symbol? You will understand that it is like a hump or zebra crossing on the road. Now, a vehicle comes, there is a hump there. Vehicle has to go up, come down, go up, come down, go up, come down, go up, come down through the road hump. Naturally, vehicle's speed will be reduced. The vehicle's flow will be obstructed by the hump. In the same way, when the current comes, current has to go up and down, up and down, up and down, up and down, and the current's speed will get slightly reduced and the flow of current will be slightly obstructed. That is the meaning which you have to visualize. Otherwise, current will not up and down inside of a resistor. Inside a resistor is simply a material. There is nothing called up and down inside a resistor. Okay. Similarly, when you see a capacitor symbol, what do you understand? When you see a capacitor symbol, you will understand that current comes all the way. Let us say electrons come all the way from this side. When electrons come all the way from this side, they don't find a path here because there is an insulating material in between the two plates of the capacitor. And that insulating material is called as a dielectric medium. Why it is called as dielectric medium? For example, let us say electrons come from this side. Electrons don't find any path. Electrons get accumulated here. Electrons cannot go back. Electrons cannot go back because there is a EMF there. There is an electromotive force which is pushing the electrons this side. So what happens is, because there are electrons here, because of the electrostatic induction, at the other plate there will be positive charges or holes. At the other side there will be deficiency of electrons. When there are more and more electrons at the left side plate, these electrons will repel the electrons which are there in the other side. So when the electrons leave this particular plate which is opposite, naturally there will be holes induced. This is called electrostatic induction. When there are holes induced, now we say that the medium in between is called dielectric medium. Di means two. Dielectric medium, we call it because there is an induction of minus and plus at both sides. There is an induction of electrostatic charge. That is when you say capacitor gets charged. And you also say capacitor blocks DC and passes AC. Why it blocks DC? Because current cannot go to the other side, electrons cannot go. Now why it passes AC? When electrons turn their direction, electrons will now come this side, and automatically at the other side there will be induction of the holes. That is when we say capacitor blocks DC and passes AC. Now, the person who made the symbol for a capacitor is genius. Even though it is two vertical lines and two horizontal lines, it indicates a lot of meaning about the functionality of the device. Same way, look at this MOSFET symbol. If you understand the symbol, you understand the device. That's all. Now, at the gate there is a p-type material, and drain and source is actually made up of the channel, that is n-type. So naturally between gate and source there is a p-n junction. That is why the arrow mark is pointing towards channel. Conversely, in the case of p-channel JFET, what is happening there is, here drain and source are again identical. Okay, but there it is, channel is p-type, gate is n-type. So this is the other side. The PN diode is from channel to gate. That is why the arrow mark is pointing outward. So my dear students, if you understand the symbol, you will understand the device. Now the summarized points for N-channel JFET. P-channel JFET is simply the converse of these points. The maximum current for an N-channel JFET is defined as IDSS, drain to source current during saturation, IDSS, and it occurs when VGS is 0 volts and VDS is greater than or equal to modulus of VP. We already know that pinch off voltage is negative and drain to source voltage is positive in case of N-channel JFET. And when you don't apply gate to source voltage, the device is completely on. That also we know. So this was already discussed earlier. This is simply a memory recall for you. Drain current is 0 when VGS is more negative than VP. Now we know that VP itself is a negative voltage, and if VGS crosses VP, then the device will be completely off. There cannot be a flow of current between drain and source. So drain current is 0 when VGS is more negative than VP. For the values of VGS in between 0 and VP, the drain current will respectively range between IDSS and 0. Which means when VGS is 0, IDSS is maximum, and when VGS is VP, IDSS is 0. So naturally, when the get to source voltage is in between 0 and VP, the drain current will be between maximum and minimum. Just remember this, when VGS is between minimum and maximum, the drain current will be between maximum and minimum. That is why JFET is a voltage controlled device. VGS is controlling the conductivity of the device. I hope you are able to view this animation. It is suddenly changing its color. I don't know whether it is because of this WebEx meeting or not. I will be sharing this PPT with you anyhow. There you can see it in reality. This animation has nothing to do with the AEC, but still I wanted you to see this particular animation. This is the internal diagram of a cathode ray oscilloscope. When you come to offline classes, you will be working with the labs. There you will be using oscilloscopes. Oscilloscopes are utilized to see the signals as such. So we are not going to discuss the construction of the oscilloscope as such, but I sincerely feel, or my sincere advice is that just understand how an oscilloscope works just by googling something. You ask Googleshwar, he knows everything. Everything in the sense, everything about oscilloscope, Googleshwar knows. So you can visit some particular websites where they will discuss about the construction of the oscilloscope or the functioning of the oscilloscope. And then you will appreciate this particular animation. I had collected this animation from internet itself. Now, transfer characteristics. In general, transfer characteristics means output versus input. Okay. Now this transfer characteristics is obtained from the output characteristics. At the right side, you will see the output characteristics, which we are already familiar. Now, for the same right side, we want to have a plot of the left side. Left side, let us say it is input versus output. At the right side, it is only output. Means x-axis is also output, drain to source voltage. Y-axis is also output, drain current. Now let us relate the right side with the input or with the get to source voltage. Now look at the x-axis. X-axis bottom, we know that the device is off. And we know that the device will be off when VGS is more than VP. So if VP is, let us say, 4 volts, VP is, let us say, minus 4 volts, at that time device is off. So at minus 4 volts, drain current is 0. We can mark a point here. Let me annotate. We can mark the first point at the left side in the x-axis, where VGS is minus 4 volts and drain current is 0, device is off. In the same way, we can mark the uppermost point. Here IDSS is maximum 8 milliampere, for VGS is 0, that is shown. So when VGS is 0, VGS x-axis at the left side is 0, IDSS is 8, we can mark this particular point. Now we got 2 points for our transfer curve. You can see that in the transfer curve, y-axis is output and x-axis is input. And it is also called as transconductance. If at all we have a formula where IDSS divided by VGS, then it is current by voltage. That is called as conductance. As it is a transfer curve, we can call it the slope of this curve as transconductance, because it is current divided by voltage. Similarly, for this particular point, VGS equals minus 1 volt. where the current is around 4.5 milliampere. When the current is 4.5 milliampere, this VGS is minus 1 volt. That can be marked here in the x-axis. You can see here. VGS is minus 1 and IDSS is 4.5. So this point can be marked. Then when VGS is minus 2, that also can be marked in the x-axis. At that time IDSS is 2 milliampere. That also can be marked. Similarly, when VGS is minus 4, VGS is 3, minus 3. When VGS is minus 3, current is around 0.5 milliampere. That also can be marked. X-axis minus 3, y-axis 0.5. So when we have these 5 points, we can join all the 5 together and we can have a transfer curve. Now you can see that this curve is non-linear. If at all you plot this curve for BJT, it will be linear because of beta. But we did not plot this curve in BJT because it was not required. Why? Because we knew beta. When we knew beta, we could use beta for our calculations. But in JFET, there is no beta. And how do we plot or how do we bias our circuits later on? How do we set a Q point? For that, we require something called transconductance. As beta is not there in JFET, and we only have to find out something called transconductance, for which the symbol given is GM. That I'll discuss later on in the future classes. But why we plotted the transfer curve is, we want to find out the relationship between output and input. In case of BJT, already we had that relation between output and input. That was beta. In case of JFET, there is no gate current. There is only gate voltage. We only have to find out the relationship between output and input. That is the reason we have to plot this curve. Now this transfer curve is non-linear. You can see that. I will stop annotating. You will see the curve clearly. You can see this curve. It is not a linear line. It is a non-linear line. That is why I had mentioned earlier, the transfer curve of JFET is non-linear, whereas the transfer curve of BJT is linear. Now, using this transfer curve, we can find out something called GM or transconductance. And using the transconductance, we can actually have the design of the biasing circuitry for JFET. And that we will be seeing how to bias a JFET circuitry, we will be working out in the next classes. With BJT, the output and input currents are related linearly by beta. But with JFET, as there is no input current Ig, the trans relation is non-linear and can be defined by Shockley's equation. The scientist William Shockley made an equation for this particular JFET. That equation is this equation. ID equals IDSS into 1 minus VGS by VP whole square. This is the equation which Shockley derived. We are not going to have the derivation of this equation in our syllabus. It is too much complicated. We are only going to use the equation which Shockley derived in our future exercises. Now remember this equation. Keep on looking at this equation and chant this equation 10 times or 20 times, and you have to remember this equation lifelong. Keep on telling as I say. ID equals IDSS into 1 minus VGS by VP whole square. ID equals IDSS into 1 minus VGS by VP whole squared. ID equals IDSS into 1 minus VGS by VP whole squared. Keep on chanting this, you will remember this formula. It is very much required for you to remember this formula. Now this formula or equation can be written